This is question 2 of the 2020 Waves exam, level 2. We've got question 2. RS sees an object to the bottom of the pool at the shallow end and reaches down to grab it. She finds the object is actually deeper than it looked to be. Name the phenomenon that causes the object to appear at a different depth. So the light bends, and that bending is called refraction. Refraction. The image or formation of the image can be represented using an array diagram. Complete the diagram above to show the image of the object. So this is kind of a tricky one because you can't really. Okay, we know the index of refraction in the water is going to be higher than the air. So I'll start from the object first. We'll just sort of do this, not pretend, but how am I going to do this? I'll just realize this question sets it up for you. If you tried to draw a ray from the eye straight ahead, you can obviously see that you're not going to get there. So we'll just sort of pretend the ray goes to about here. And then we're going to draw our normal. So our normal is perpendicular to the boundary. And then this angle here, we'll just call it theta 1. Theta 2, because the light ray is going to slow down and it's going to bend towards the normal. So it's going to, I mean, we can overdo it a little bit, but it's going to bend, that'll do, like that. And we can pretend, the light rays come from the object, that's how your eye sees it. So we'll chuck in some arrows like that there. And because it's an object, I mean, we'll try and like draw more than like just one arrow. So we'll have another piece of light going up and show how it's sort of formed on the eye, like so, and it's going to bend the same amount. Hopefully that's about there, looks about right. There you go. And I'll chuck in my other normal, like so. We got, this is another theta. And you'll see the object is sort of forming on the eye like so. Yeah, I'm not that good at drawing. But anyway, use physics principles to explain, to give full explanation how the process in part B causes the observer to see the image at the position located by a diagram. So you could say, as the light travels through the water, well, as it hits the boundary or transitions from the boundary, it speeds up and it bends away from the normal. This change in speed, it causes it to bend away from the normal, which then bends towards the eye because the eye is just in that position, which gives the apparent, like the eye thinks, because the eye thinks it like travels in straight lines, so it thinks the object is over here. And you realize that this distance is actually further than this distance here. So that's why it looks like that. I'll try and pause and write a good answer. So I've said, as the light crosses the water-air boundary from the object, it speeds up. As the light crosses the boundary at an angle, it changes direction, bending away from the normal. If it didn't cross at an angle, it would just slow down, not change direction. I said the brain perceives the light as if it had travelled in a straight line, so the object is assumed to be to the right of the object and further away. Your brain assumes the object's over here somewhere. That's where your brain... It's not the eye that does that, it's the brain. And it's just because of the way your perception works in the brain, which is kind of weird and wacky. Anyway, pull that down a little bit. Mia jumps into the deep end and looks up and sees the bottom of the pool reflected above her, as shown below. I'm kind of annoyed that I didn't print this out in colour, but anyway. This you can't find on the NCEA website. Because I'm a teacher, I can get access to it. I don't know if it's copyrighted or not, but the link's in there. I mean, it's common use, so it should be fine. I've got in the description, there's a link to the answers, and it's got the coloured version of this. Identify the phenomenon that's taking place in this photo. It's total internal reflection, because you've got the bottom of the pool looking at the top. So total internal reflection. Write a comprehensive explanation for how this phenomenon occurs. Include the condition condition is required in calculation of the critical angle. So we'll do the calculation of the critical angle first, because it's probably just a bit easier. So you've got, I'll draw a little picture because it's probably going to be easier. Here we've got water. I'll say this is water, this is air. We've got light trying to escape, except for, like, it bends away from the normal as it goes into air, but it gets to a point where it bends so much it hits 90 degrees, and at that point it just totally internally reflects. Well, that should just be a solid ion. So we're going to call the water's N1, the air is N2 because it's medium 2. This angle here is theta 1, and the outgoing angle is going to be 90 degrees. So that's theta 2 is going to be equal to 90 degrees, and past that point the light just reflects. Everything up to 90 degrees, the light would sort of get through and be off at a really, really steep angle. So what we're going to have is we're going to have Snell's law. You can look that up in the formula sheet. N1 sine theta 1 is equal to N2 sine theta 2. And now we just put in for what is what. So water is 1.33. 1.33 sine, and this is technically the critical angle, so I'm going to change that to theta c, and that is going to be equal to 1, because the refractive index in air is 1, sine 90. But if you do sine 90 in your calculator, I'll just turn my calculator on. I'll just check if it's on it's on degrees. Cool. You need to always make sure your calculator's on degrees, not radians. Sine 90 equals 1. So we can just cross this out and just have 1. And 1 times 1 equals 1. So it equals 1. In other words, 1 over 1.33 would equal sine of the critical angle. Sure, I'll just do it. Equals sine of the critical angle. In other words, the critical angle is equal to sine inverse, because you take the inverse of both sides, it cancels it out. 1 over 1.33. There you go. I'll do that on a calculator. Shift sine. What do we got? 1 over 1.33. Bracket. Sweet. 48.7 degrees. 48.7 degrees. That's it. That's the critical angle. I suppose you could probably round that up to 2SF, because we've got... No, we don't need to. Well, you wouldn't have known the angle anyway. That'll do. Right, so I'll pause and then I'll write out the description. So I've said when light moves from a medium of high refractive index to low refractive index, it bends away from the normal. I should already put the caveat, as long as it's coming in at an angle. This bending will occur up to 90 degrees. After that, light reflects. The incoming angle at which this occurs is known as a critical angle. In this case, 48.7 degrees. And that's it.